In this video, we'll try to understand how to compute the linear velocity of an object that is undergoing uniform rotational motion, okay, with an angular velocity of omega. So let's say the object is located here at point P and it has coordinates of x and y, and this point P, when connected to the origin O, makes an angle of theta with the x-axis. So we can use vectorial notation to write the position vector of the point P. The position vector of point P is vector r is essentially xi I hat plus y j hat in vectorial notation, and here x is nothing but r times cosine of omega t, okay, I hat plus r times sine of omega t j hat. So we are assuming that the particle is moving in a circle of radius r. Okay? So that's, and its angular velocity is given to be omega. So now let's do this. Let's find the derivative of the position with respect to time. So if we write dr over dt, okay, and that is equal to the velocity vector, and that equals minus r omega, okay, sine omega t I hat, okay, plus r omega cosine omega t j hat, right? So if we find the magnitude of the velocity vector, okay, and call that a scalar linear velocity, that is nothing but minus r omega sine omega t square plus r omega cosine omega t square with the square root of on top of the entire right hand side. So what we can do is we can take r omega outside the square root, and we are left with sine square omega t plus cosine square omega t with a square root on top, okay, and this entire expression is just 1. The square root of 1 is 1, so we have the linear velocity equals r times omega, okay. So now let's take the double derivative of the position vector. So we do it this way: d2r over dt square equals, this is dv over dt, okay, and that is the acceleration vector, and that equals minus r omega square cosine of omega t I hat plus r omega square, actually that would be a minus r omega square sine omega t, okay, j hat. So now what we can do similarly is to find the magnitude of the acceleration and call that a scalar number for acceleration. That's equal to r omega square, and the same way cos square omega t plus sine square omega t, and we know that this is 1, okay, so this is nothing but omega square r, okay, and here we know that v equals r omega, okay, from the equation that we just derived. V equals r omega, and therefore omega equals v divided by r. So therefore the acceleration is v square divided by r square times r equals v square divided by r. Okay, and therefore the centripetal force, okay, the centripetal force equals mass times acceleration, and that is m times v square over r. Okay, so this is the well-known formula for the centripetal force. So let's recap what we just did to so that we can understand what how to derive this from scratch. So we have a particle that's moving in a circle, uh, and its current position is point P with coordinates of x and y, and the line between the point P and the origin makes an angle theta with the x-axis. Makes an angle theta with the x-axis, and this particle moves in a circle of radius r. Okay, so now, and this is moving with a constant angular velocity equals omega. So we can write the r, the position vector, as x times the unit vector along the x direction plus y times the unit vector along the y direction. And so now we know that uh, the 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 x coordinate is nothing but r times cosine theta. Okay, and this is nothing but r times cosine of omega t, where omega is the angular velocity. Okay, so essentially theta is the angular velocity times the time. So angular velocity is in the units of radians per second, and the time has units of seconds. So the theta has units of radians. Okay. So similarly, we can write y as r sine theta. So and theta equals omega t. So we have r times sine omega t. So the value for the position vector is r cosine omega t I hat plus r sin omega t j hat. We take the derivative of the position vector with respect to time to find this expression, knowing that the derivative of cosine is negative sine and the derivative of sine is a cosine, and we use chain rule here. Okay, so we get minus r omega sine omega t I hat and r omega cos omega t j hat. So if you want to find the magnitude of the velocity vector, okay, we add the sum square of the components and we end up with r omega. So the linear velocity is r omega. Okay, and here again we differentiate this above expression one more time with respect to t to find the acceleration, and that equals minus r omega square cosine omega t I hat minus r omega square sine omega t j hat. We take the magnitude of the acceleration vector, and we by adding the sum squares of the two components, and we find that this is equal to omega square r. Okay, and we know from here that v equals r omega. So therefore omega equals v over r. So we find that the value of acceleration is v square over r, and therefore the centripetal force required to keep the object in motion is m times a, that is mv square divided by r. Okay, so the other thing to note is that the linear velocity is r omega, and omega, you know, when the linear velocity when the angular velocity is uniform, we can write omega as 2 pi divided by t, where t is the time taken for one complete revolution. Okay, revolution, and therefore v equals 2 pi r divided by t. Okay, so essentially 2 pi r is the circumference of the circle, and t is the time to traverse the circumference one time. Okay, so the distance divided by time, that gives you linear velocity. So all these equations are self-consistent. Okay. So I hope we understand how to derive these expressions for the linear velocity and the centripetal force from scratch.